Hello, it's Dave Giles here for the first lesson of Cambridge IGCSE Physics Unit 3 Waves. And today we're looking at an introduction to waves where we're going to cover some of the basics, where we describe key features of transverse and longitudinal waves. So some of the key words we're going to use today are transverse, longitudinal, energy, oscillation, parallel, and perpendicular. And hopefully you better use all these words correctly in the terms of waves by the end of the lesson. So first of all, we need to look at what an actual wave is. So waves transfer energy or information from one place to another, but without transferring matter. So without particles necessarily moving from A to B, they transfer energy. Waves are caused by vibrations or oscillations. Vibrations are regular backwards and forwards or up and down motion, like an actual wave you might see here. So moving your hand back and forward is like an oscillation, and it can also be represented here like a sine or cosine wave, a graph, sorry. So we split waves into two main types. The first one is transverse. So this here is an example of a transverse wave. They move up and down. The energy is transferred from left to right or right to left, but the particles in this case, or the wave, moves up and down. It doesn't necessarily need particles to move. Can travel through space and can travel very quickly. So light, for example, travels at this many meters per second. That's 3 times 10 to the 8. That's 3 with 8 zeros, meters every second. Next up, we've got longitudinal waves. These move backwards and forwards, as you can see here, and they travel through substances, so that they need a medium, it's a term we use, for them to actually travel. So, such as water and air, but space, which is a vacuum and has no particles, it cannot transfer energy. So longitudinal waves don't travel through space. So transverse waves. A Mexican wave, if you ever seen one of these going around a stadium, is sort of similar or to a transverse wave. So the particle movement is the same as the direction of each person in the Mexican wave. So if you think of a Mexican wave, each individual person is moving up or down. But the energy movement is the same as the direction of the crowd. So the crowd appears to be moving from left to right or right to left. Okay. So here I've got some key features of a wave. So this here is a wave, and I've got A, B, C, and D. I want you to label a wavelength. Now, this is a word a lot of people struggle to pronounce. It's pronounced trough, peak, and amplitude. As some extra there, I want you to add on which way the wave oscillates, so the way it moves, and which way does the energy move. Okay, draw that on the diagram. And what I'm going to do as well, in a few seconds, I'm going to put on the definitions of these key words. That you can use that to help you. But if you can do it without the help first, that's brilliant. Okay. So I've put the definitions on here to help you out now. So the first one, A, is the distance from the middle bit or the center point to the peak. So, or the top part here. So we haven't defined peak yet. So that is the amplitude. So A here is the amplitude. B is the distance from one of these top bits to the other top bit. That is the wavelength. This bit here is the bit at the very bottom of the wave. That's the trough. And this bit here, the bit at the top, is the bit we call the peak, the highest point in a wave. And which way does the wave oscillate? So it oscillates up and down, but the energy movement goes the other way. So we say the direction of energy is perpendicular to the direction of the oscillation of the wave in a transverse wave, which you can also see here. Now, you can see I've got some individual red particles, and you can see each individual particle or each part of the wave is just moving up and down. It's not moving left and right, it's just moving up and down. The energy, though, is transferred from left to right or right to left, as I mentioned earlier. So this bit here is the equilibrium position. So it's the center of the wave. So this we normally class as the 0 meters if we're measuring the amplitude. This here is maximum displacement, also known as the peak. And this here is maximum displacement negative, also known as the trough. And the wavelength is going to be the distance from the equilibrium position to the maximum displacement, or the equilibrium position to the maximum displacement negative. Okay. Okay, 1 second. Okay, so now we're going to move on to looking at a longitudinal wave. So this here is an example of a longitudinal wave, possibly a sound wave. It's one example of a longitudinal wave. So what I've done here is I'm measuring the distance along this wave. And if you notice, about every 1 meter, there's a big change. So here you see I've got areas where I've got loads of particles, and here where I've got very, very few particles. In fact, I actually count the particles in each section. And if I was to plot a graph of the number of particles against distance, I'll get something that looks a little bit like this. So in a longitudinal wave, the wavelength is distance between two compressions. So this is a compression here. It's because the particles are compressed together. So at 0 meters here, at 2 meters, that is a compression, or two rarefactions. So a rarefaction is a bit where the particles are actually a little bit more spread out. So you can see it goes compression, rarefaction, compression, rarefaction. Just a little note, always start at the same point. So don't measure from here to here to get the wavelength. If you measure from this end of the compression, go to this end of the compression there as well. So, little summary, transverse wave summary first. So the direction of the vibration of particles up and down here, but the direction of propagation, that is basically the direction that the wave is moving is at 90 degrees to the direction of the vibration of the particles. Or like I say, it doesn't always need particles. The direction of vibration of the particle is perpendicular to the direction of energy transfer. It consists of peaks and troughs, or labeled at crest, but we generally use the term peak. And some examples are light waves, water waves, and seismic S waves, which you get in earthquakes, which if you study geography, you might know a little bit about them already. And some examples of longitudinal waves are sound waves and seismic waves, which are also you will look at in geography. So the summary of what they actually do first, the direction of vibration of particles is the same as the direction of propagation of energy transfer. Okay. So we can say direction of vibration of particles is parallel to the direction of propagation of energy, consists of compressions and rarefactions. Compression here, and it's the rarefaction, which this one here might possibly be something like a slinky. You might do an experiment in school with a slinky where you push one end forward and you can see the wave moving along. And the examples are sound waves and seismic P waves, with P standing for primary. So I gave 2 examples there with relating to earthquakes. And I'm going to go into them in a little bit more detail here as well, because you do need to know about P and S waves, although you only need to know very basic information for physics. So this here is the structure of the Earth. You've got your inner core, which is solid, and then you've got your outer core here, which is a liquid, and then you've got your mantle after that. And then finally the crust. So P waves, the initial shock waves, they push and pull material as they move through Earth. So here you can see the direction of propagation is the same as the direction of the particle movement. So this here is a longitudinal wave. Whereas the secondary waves, they arrive minutes later and pass through the crust side to side. You can see here we have a transverse wave. So P waves arrive first in an earthquake. They are longitudinal, can travel through solids and liquid mediums, and they can travel very quickly. Whereas, 2 seconds. Sorry. We can learn about the Earth's structure through examining S waves and P waves. S waves are transverse and can't travel through liquid. P waves can travel through the liquid core, but refract as they change speed in different density materials. We will look at refraction in a few lessons' time. You don't need to know a huge amount about it though for the P and S waves. This here is a short diagram of what they look like. You can see that the S waves have to avoid going through or rather, they can't travel through the core, whereas the P waves can go through it, but they do change direction a little bit when they travel through. Okay, so here are some paper 2 multiple choice questions. Which row shows the amplitude of the wavelength of the wave? As usual, pause it yourself, think about it, work it out, and I'll give you the answer in a few seconds. So let's have a look at the amplitude first. Now, from peak to trough is 2 meters, but the amplitude you always measure from the middle to the peak or to the trough. So if we go from the middle here to there, it's going to be half of 2, so the amplitude is going to be 1 meter. So I know straight away my answer is either A or it's going to be B. The wavelength here is a little bit more tricky. So it's labeled 4 meters, but there I've got the wavelength is from here to here is one wavelength. And then from there to there is another wavelength. So we've actually got 2 wavelengths here. So the wavelength will be half of this. It'll be 2 meters. So 1 meter amplitude, 2 meter wavelength. So the answer is therefore A. Question 2. The diagram shows 4 sources of waves. Which source generates longitudinal waves? Now, a lot of people actually got this question wrong when I've used this in lessons before. A lot of people are saying the radio transmitter, but the radio transmitter receives an electromagnetic wave, which is which is transverse. So, sorry, not transmitter, sorry, transmits the wave, sorry, not receives. So the only one that's actually generating a longitudinal wave is the one that's generating sound itself. So that would be the loudspeaker. It would be C. Next question. How waves are sent along 2 long springs, X and Y, you can see here. How should the wave motion X and Y be described? Okay, so side-to-side movement, direction of wave travel is perpendicular to the movement. So this one here, X, must be transverse, whereas here, the direction of wave travel and the movement are parallel with each other. So that is longitudinal. So the answer is therefore C. Question 4. An earthquake wave travels through the solid surface of the Earth from east to west. The solid surface vibrates in north-south direction. How can the earthquake's wave be described? So you can see here the wave is traveling east to west, and the vibration is north to south. So they're at 90 degrees to each other or perpendicular. So therefore, it will be transverse. Question 5. Which wave has an amplitude equal to half of its wavelength? Okay, so we're going to just work our way through them here. A has got an amplitude of 1 meter, and it's got a wavelength. So the way you can see the wavelength is by looking at where it starts here. It goes up, comes back down. That's half a wavelength there. Goes back up, and is now back going up the same direction which originally came here at 1 meter. So displacement and say amplitude and wavelength here are the same, so it's not that. We'll look at this one here. I'm going to see next. So here we have an amplitude of, it looks like about 0.5 centimeter. We've got a wavelength of 4 centimeters, so it's not that one. D, we've got an amplitude of 1 meter, say 1 centimeter, and also an amplitude of 1 centimeter, so it's not that. So B here, we have an amplitude of 1 centimeter. We have a wavelength of, so I'll start here, I'll start tracing it. Up, down, back to where we started here, 2 centimeters. So yes, now the amplitude, sorry, is half of its wavelength, so the answer is B. Okay, and the last multiple choice question. The diagram shows a ball floating in a tank of water. Which diagram shows the movement of the ball as the wave passes? Now, water waves are transverse. So the ball, so it's moving this way, the ball will move at 90 degrees to it, and it'll start from its equilibrium position, and it'll move up, and it'll move down, as you can see through this little bit here. So therefore, it is D. Okay, and that completes today's lesson, describing key features of transverse and longitudinal waves. The next lesson, which I'm going to upload straight away, will be on the wave equations. So thank you very much, everyone, and I will see you in the next lesson.